Hello, welcome to the last lecture of Solitons. So what I will do today is to give a summary of the inverse scattering or reassembly, which is the third part of this procedure that we call the inverse scattering method to solve the initial value problem for the KdV equation. So because this is the last lecture, I would like to make sure that I get to a sensible bottom line. I hope you'll forgive me if for today I will simply speak over the lecture notes rather than writing down formulae and words, which would take me longer. Of course, I will not expect you to be able to reproduce all of this during the exam by yourself. So, okay, let me start by reminding you the whole idea of the inverse scattering method. So we wanted to solve the so-called initial value problem for the KdV equation, which is a nonlinear partial differential equation of the first order in time. And so we need to specify some initial data, which is the profile of the field U, which is a function of x at a fixed initial time, let's say time t equal to 0. And the initial value problem is to determine the solution u of x and t at later times, given the initial data. So because the KdV equation is nonlinear, it is hard to follow this, to solve this initial value problem directly. So what we do instead is we take a roundabout route, which, however, allows us to split the problem into three simpler and solvable problems. So in particular, there were three steps, two of which we have already discussed. So first step was to disassemble the initial data into some equivalent scattering data. That was step A. So let me remind you what that looked like. So what we did was to take the initial data, so the profile of the KdV field at time equals 0, to be up to a minus sign, the potential in a time-independent Schrödinger equation, as you see here in equation 9.1. And then we looked at the solution of this equation, which is also an eigenvalue problem. And in particular, the two classes of eigenvalues and eigenfunctions. So there is a continuous part of the spectrum, in which case k squared is positive and all positive values of k squared are allowed. And correspondingly, we find solutions of a scattering type. So here in equation 9.2, I have a scattering solution which describes a unit flux of waves coming in from minus infinity, and then part of the waves are reflected back towards minus infinity, and part of the waves are transmitted through the potential towards plus infinity. So that described the eigenfunctions for the continuous part of the spectrum. On the other hand, there is also a discrete part of the spectrum which corresponds to negative values of k squared. So I set k equal to I mu here. And only for specific values of mu, there exists a bounded solution of the type 9.3, where here mu is positive, and you see that the asymptotics make sure that the solution is bounded. In particular, it decays to 0 exponentially at plus and minus infinity, with coefficients Cn and Dn for the asymptotics that can be determined once we impose the following normalization condition. So the scattering data here consists of the eigenvalues of the Schrödinger problem, as well as essentially the asymptotics. So we can either look at the asymptotics at minus infinity, in which case we look at the reflection coefficient R of k and the coefficient Cn together with the discrete eigenvalues mu n. Or we could look at the asymptotics at plus infinity, in which case we would focus on the transmission coefficient, the coefficients dn, and the same eigenvalues mu n. So that was step one here. And next we saw that thanks to this idea of the Lux pair and the Lux equation, actually it was much easier to evolve forward in time the scattering data than it was to evolve forward in time the initial data of the KdV equation, essentially for two reasons. So the first reason was that the Lux equation implied that the eigenvalues of the Schrödinger equation, say mu n and k, do not change with time. And secondly, we saw that the time evolution of the reflection and transmission coefficients, or the coefficient Cn and Dn for the bound state solutions, was governed by an equation which was a linear equation. And moreover, it was completely independent of the potential, because we only worried about the asymptotic region where the potential goes to zero. And so we found, in particular, the time evolution, say, of the reflection and transmission coefficients as in equation 9.36, and of the coefficients Cn and Dn for the bound state solutions. So that solves part B of the problem, which was the time evolution of the scattering data. So now we have scattering data at a later time, t, and what we would like to do next, and that's what I will try to explain today, although rather briefly, is how to reassemble the scattering data at time, well, at any given time, in particular at time t, back into the potential of the Schrödinger problem, or equivalently, the KdV field at time t. So we call this reassembly or inverse scattering. So now let me move to the notes here. So that's what we would like to do today. Reconstruct or reassemble the KdV field u of xt, or equivalently the Schrödinger potential, which is equal and opposite, from the scattering data at x going to minus infinity. So that will consist of the reflection coefficient for the continuous part of the spectrum, and the discrete eigenvalues, and the coefficient Cn for the discrete part of the spectrum. So, as I have already remarked in an earlier lecture, it is actually quite surprising that this inverse scattering is possible at all. So, to borrow a famous sentence in a different but related realm of mathematics, this problem is like being able to hear the shape of a drum, that is to reconstruct the shape of a drum head from the sound harmonics that it makes. So here the harmonics are essentially the scattering data, and the shape of the drum that we want to reconstruct is the potential, the Schrödinger potential, or equivalently the KdV field. So this is highly non-trivial, but luckily this problem had already been solved for equations of the type that we're interested in by Marchenko a few years before Gardner, Green, Kruskal, and Muir realized that this was relevant for the KdV equation. Okay, so what I'm gonna explain today is essentially, essentially outline today is the various steps in this inverse scattering method. But before we get there, let's first look at perhaps a simpler case, which we can take for motivation, which, as we'll see in a second, is relevant for a Schrödinger problem with zero potential. So here we start from a wave equation for a function phi of two variables, x and z. So the wave equation is phi xx minus phi zz equals to 0, equation 11.1. And we've seen a number of ways to solve this equation. In fact, we can write down the most general solution following D'Alembert. And one way that will be relevant today is that of the Fourier transform. So in particular, we can take Fourier transform with respect to the variable z and replace it by a conjugate variable k. So then we write phi as an integral over k of its Fourier transform with respect to z, psi function of x and the conjugate variable k times a plane wave factor e to the ikz. So normally, and similarly, there is a formula, an inverse formula for the Fourier transform psi in terms of phi. So normally, I use tilde for the Fourier transform, but here I am using psi because when you rewrite the wave equation 11.1 in terms of its Fourier transform psi, the equation becomes 11.3, as we see here. So we've done this exercise already in the past. And as you can see, this is essentially the same as a Schrödinger equation with a time-independent Schrödinger equation with energy equal to k squared and the potential V equal to 0. And since usually we adopt the letter psi for the wave function in the Schrödinger equation, that's why I use psi for the Fourier transform of phi. So the free time-independent Schrödinger equation 11.3 is the Fourier transform of the wave equation 11.1 with respect to the dual variables or conjugate variables z and k. Okay, so now suppose that we want to solve the original wave equation for phi. Well, we can do it by solving equation 11.3, which is also something that we have done. But what I will focus on today is solutions of equation 11.3, which obey the asymptotics in 11.4. So in particular, we require that psi goes like exponential of minus ikx as x goes to minus infinity. Okay, so like a fixed plane wave, but only as x goes to minus infinity. Okay, so how do we obtain a general solution to equation 11.3, which obeys the asymptotics 11.4? Well, we can use the formula here in the second line of 11.2. Here, the original field phi of x and z appears in the integrand. And so in particular, we can choose phi to be equal to a delta function of x minus z plus a function k, which I will call the integral kernel, which is a function of x and z, where we require essentially two things. So one is that we require that k, this integral kernel, vanishes if z is larger than x. And secondly, we require that k is a solution of equation 11.1, which was the wave equation. Okay, so essentially we're superposing a delta function plus a certain solution of the wave equation, which vanishes when z is larger than x. So why does this do the job? Well, first of all, when we plug 11.5 into the second line of 11.2, so the delta function term will select z equal to x inside the integral, and that produces exponential of minus ikx here in the expression for psi. Whereas k here in 11.5 remains integrated over z, but because k vanishes when z is larger than x, then we have an integral over z of k times exponential of minus ikz, where the range of integration is only over z less than or equal to x, so from minus infinity to x. It's easy to check that this is a solution of equation 11.3, well, essentially because exponential of minus ikx is a solution, and the integral is also a solution because we require that k is a solution of that equation. And secondly, equation 11.7 has the correct asymptotics that psi goes to e to the minus ikx as x goes to minus infinity, because when we take that limit, the range of integration here vanishes, and so the integral disappears, and we're just left with the first wave factor, this oscillatory exponential e to the minus ikx. So what we're going to do next is to try and adapt some of this logic to the problem that we're interested in, which is a time-independent Schrödinger equation similar to 11.3, but with the difference that now we have a potential. So we want to solve the inverse scattering problem eventually, but we'll get there in a few steps. So we want to solve the inverse scattering problem for the time-independent Schrödinger equation 11.8, which has the potential V, which we will, as usual, eventually identify with minus the KdV field at a fixed time. As I discussed already quite a bit this term, we're actually interested in scattering solutions and also bound state solutions, which can be obtained from them. But to construct them, it's convenient to use some other solutions which have a different normalization. These are the so-called Jost solutions, psi plus or minus of x, which so they're a function of x, which depend parametrically on variable or parameter k, which will be the wave number, and they're defined by the asymptotics. So psi plus is a solution which asymptotes e to the ikx at plus infinity, whereas psi minus is a solution that asymptotes e to the minus ikx at minus infinity. So this is not very visible. So here x goes to minus infinity. So in particular, psi minus, which goes like e to the minus ikx at minus infinity, is the analog of psi in the previous simpler example where the potential V vanished. Why do I say that we can reconstruct the scattering solution for this from these Jost solutions? Well, that's expressed by equation 11.10 here. There are two equalities here. So psi k is a scattering solution with a unit flux of waves coming in from minus infinity. So the two equalities essentially fix the asymptotics at plus infinity and minus infinity. So let's first look at the first equality. So that states that psi k, the scattering solution, is T of k, the transmission coefficient, times the Jost solution psi plus. So this ensures that when x goes to plus infinity, the scattering solution asymptotes the transmission coefficient times exponential of ikx, which is precisely here the asymptotics of the positive Jost solution. Instead, the second equality essentially imposes the asymptotics at minus infinity. So we have two terms here. So psi, and only the negative Jost solution, psi minus, appears. So the first term will asymptote, because of complex conjugation, exponential of ikx as x goes to minus infinity. That's the those are the incoming waves with unit flux. And the second term, which is multiplied by the reflection coefficient, goes like exponential of minus ikx, and these are the reflected waves. So we see that from this formula that from the Jost solution, we can reconstruct the full scattering solution psi k. And in fact, the Schrödinger equation essentially guarantees that the two expressions agree, although I'm not showing this now. Okay, so in fact, eventually we want to reassemble the potential V of x from the scattering data, which is specified by the asymptotics at minus infinity. So we can simply focus on the Jost solution psi minus, which had the asymptotics e to the minus ikx at minus infinity. And as we did earlier here, in the case of the wave equation or the free time-independent Schrödinger equation, we're going to write the Jost solution in the same way. So we assume the Jost solution psi minus to be exponential of minus ikx plus the integral over z of an integral kernel k, which is a function of x and z, times exponential of minus ikz. And yes, we assume that the integral kernel vanishes when z is larger than x. So this integral here runs from minus infinity to x, as we did previously. So expression 11.11, for the same reason as before, ensures that the asymptotics of psi minus is e to the minus ikx when x goes to minus infinity, in which case the integral disappears. Now we want to make sure that expression 11.11 actually solves the Schrödinger equation with potential V that I wrote here in 11.8. So what we'll have to do is to plug the integral expression 11.11, which involved the integral kernel K, into the Schrödinger equation. And one can simplify the result by doing some manipulations, in particular integration by parts. I will not really go through the details here. You can essentially either, well, trust me, or you can check the computations as an exercise. So the idea there is that the expression simplifies when you integrate by parts a few times, especially you can rewrite the exponential of minus ikz as being equal to its first or second derivative with respect to z up to a prefactor. And then you can integrate by part to move the derivatives to act on the integral kernel K. And in doing that, you would generate some boundary terms, but we are going to assume some boundary conditions for the integral kernel K. So we assume that K and its z derivative tend to 0 as z goes to minus infinity. Okay, so when you do that, it's not too difficult to find the expression for psi minus and its second x derivative in equation 11.13. So the details are not too important here. So it still involves integrals of derivatives of the integral kernel, and then there are some extra terms, some of which come out of this integration by parts, which also might involve some derivatives of the integral kernel with respect to x or z, with z evaluated to be equal to x at the end. Okay, so the details here don't really matter. So the point here is that we can plug this expression for psi minus and its second derivative into the Schrödinger equation with potential B. And when you do that, you obtain an expression which is the one that you read in 11.14. So we have two terms here on the right-hand side, and there's some has to be equal to 0. So first we have the quantity in bracket, which is multiplied by e to the minus ikx. And then there is also this integral where we have an integral over z of e to the minus ikz times a differential operator acting on k. So of course here, so we just want the sum to vanish, but we can solve this equation easily if we require that both the factor in bracket and the integrand here vanish. So that gives us equation 11.15 and 11.16. So 11.15 is the equation that we obtained by requiring the integrand to vanish. So it tells us that the second x derivative of k minus the second z derivative of k minus the potential v times k vanishes, where k is non-zero, which is when z is less than x. And the second equation comes from setting to 0 the quantity in bracket, and essentially allows us to determine the potential v from the integral kernel k. So we have to set z equal to x and compute the derivative with respect to x multiplied by 2, and we get the potential. Okay, so let me make a couple of comments here, or maybe 3 comments on this equation. So comment 1 is has to do with equation 11.15. So as you can see here, so the first 2 terms, so if the potential were equal to 0, then we would get the first 2 terms would give us just the wave equation, okay, that we encountered earlier on when we started from phi. Here, okay. And there we saw that this wave equation was the Fourier transform with respect to z of the free time-independent Schrödinger equation 11.3. So now instead we started from the time-independent Schrödinger equation 11.8, which involves the potential, but still we can Fourier transform or inverse Fourier transform with respect to k and trade it for a conjugate variable z, and we get an equation which is precisely the type of differential equation which is solved by k in equation 11.15. So it's a wave equation deformed by a term which is equal to the potential times k. So equation 11.15 is nothing but the Fourier transform with respect to z and k of the original time-independent Schrödinger equation with potential v. So that was comment 1, remark 1. And remark 2 is that the potential v of x can be obtained in two ways. So either we can use equation 11.15, so once we know the integral kernel k, or we could use equation 11.16. So it's not entirely obvious at first sight that the two equations are compatible, but it's not hard to check that the two equations give the same potential v. And finally, the third comment here is that up to now, so we haven't really done inverse scattering yet, so we can still think of this as direct scattering. So really here we started from the Schrödinger equation 11.8. So we're given the potential v, and now we can solve equation 11.15 with the boundary conditions 11.12 to determine the integral kernel k. And then we plug that integral kernel k into equation 11.11 to find the solution, the Jost solution psi minus of the Schrödinger equation 11.8 with potential v. Okay, so that's still, and from that, using equation 11.10, we can obtain the scattering solution psi k. So that's still direct scattering. Given the potential, we find the general scattering solution and not just their asymptotics. But what we want to do instead is to go in the opposite direction and do inverse scattering. So what we want to do instead is to reconstruct the potential v of x given the scattering data at x going to minus infinity. Okay, so that's what the problem that we want to solve using in this inverse scattering or reassembly step. But so we will use some of the concepts that I introduced so far, in particular this integral kernel k that satisfies equation 11.15, the Fourier transform of the Schrödinger equation with the boundary conditions 11.12 will appear prominently, and also we'll use eventually equation 11.16 to reconstruct the potential. Okay, so let's describe briefly what we're going to do. So because of lack of time and also because it's rather long and tedious, I will not go through the derivation of this recipe, but I will just state it for you. And if we had time, then I would have gone through a number of examples to see how this recipe can be used to do inverse scattering explicitly, but we won't have time for that. So if you are interested in the derivation of the recipe that I'm gonna introduce in a minute, you can read it in section 3.3 of the book by Drazin and Johnson. So with the only caveat that in that book, everything is phrased in terms of scattering solutions with waves that come in from plus infinity, and in terms of the asymptotics at plus infinity rather than minus infinity. So one has to change a few formulae that I have done in the notes, but the logic is the same. So I will keep working with the scattering solution with waves, unit flux of waves coming in from minus infinity, some of which are reflected and some of which are transmitted. The upshot of this recipe is as follows. So it goes in 3 steps. So step 1 is the following. So given the scattering data, which consists of the reflection coefficient for the continuum or scattering states, and of the eigenvalues mu n and the coefficient Cn for the asymptotic set minus infinity for the discrete part of the spectrum and bound states, we can construct a function capital F of an auxiliary variable xi as in equation 11.17. So we see that there are essentially 2 types of contributions to the right-hand side. So the first contribution is the Fourier transform of the reflection coefficient R of k. So that is associated to a continuum in the spectrum and to the scattering states. So then there is also discrete sum from small n from 1 to capital N, which is the number of bound states, of a real exponential where the exponent here is mu n times xi. So that's analogous to the e to the minus I k xi that appear in the Fourier transform of the reflection coefficient. So when you set k equal to I mu, you get the exponential of mu xi. And then instead of the reflection coefficient, we have the square of this constant Cn. Okay, so given the scattering data, you can construct, in principle, this auxiliary function of a variable xi. So now, why is this function useful? It's useful because the integral kernel k that we're interested in, so the kernel that solves equation 11.15, so the Fourier transform of the Schrdinger equation, together with the boundary condition 11.12, can be shown to satisfy an integral equation, which is the Marchenko equation 11.19, that involves the function capital F of xi, the auxiliary function that we constructed above in terms of the scattering data. So this, okay, looks like a complicated equation, this Marchenko equation. It's an integral equation. But in principle, we can use it once we know the scattering data, and so we construct the function f of xi. We can then solve the Marchenko equation to determine the unknown integral kernel k, which is a function of x and z, which again we take to vanish when z is larger than x. Okay, and finally, once you have the integral kernel of Marchenko equation k of x and z, we can determine the Schrödinger potential using one of the equations that we wrote earlier. So by setting z equal to x and computing its x derivative. So that's the same as the equation 11.16 that we obtained earlier. And if we're interested actually in the KdV equation, then the KdV field is minus the Schrödinger potential as usual. So just to summarize again, so we start from the scattering data at minus infinity, given by equation 11.18. We plug it in 11.17 to construct this auxiliary function f. And this function f can be shown to appear in the Marchenko equation that we can use to determine the integral kernel k, which in turn we can use to determine the Schrödinger potential, or equivalently, the KdV field. Okay, here there is a comment there where tells you how the formula look like when you look at asymptotics at plus infinity, as in the book by Dresden and Johnson, but let's not worry about that. Okay, so essentially, this three-step procedure in this page tells you in principle how to do this inverse scattering. So reconstruct the shape of the potential V of X or the KdV field U at a given fixed time from the scattering data of the auxiliary time-independent Schrödinger equation at that same time. But of course, now we know that time dependence of the scattering data, because we worked it out in a previous lecture, and in particular I showed you formula before. So in particular, when we look at the asymptotics of the eigenfunctions of the time-independent Schrödinger equation as x goes to -infinity, we have to worry about the reflection coefficient and the coefficient Cn. In addition, there are also the eigenvalues mu n, but those do not change with time because of the Lax equation. So their time dependence, which we computed in a previous lecture, is given again in equation 11.21. So now what we can do is to take these expressions here and plug them in the formula for the auxiliary function f of xi. And that will allow us to essentially solve the inverse scattering problem, which is going through these three steps for any value of the KdV time t. Okay, so let's do that. So I'm going to take equation 11.17 and now plug in the reflection coefficient at KdV time t and the coefficient Cn at KdV time t to obtain a function f of xi at KdV time t. So that's what I wrote in the first line of 11.22. And then in the next line, I'm just using the time evolution of the reflection coefficient and the coefficient Cn, which we computed in a previous chapter and which I wrote in 11.21. Okay, so we get the expression here in the second line, 11.22, which again involves an integral over k. So some Fourier transform of the reflection coefficient, and then a sum of exponential terms coming from the discrete part of the spectrum. And sorry, I see a typo here. This upper value here for the sum should be capital N, the number of bound states, not infinity. Okay, so then, you know, it might be hard in practice to compute explicitly or analytically to find a closed formula for the function f of xi at all times t. So that's in 11.22. And then to plug it in equation 11.19, the Marchenko equation, find the integral kernel k of x and z at all times t, and eventually take its x derivative once we set x equal to z to obtain the potential V of x or the KdV field at any KdV time t. So it might be hard to obtain this formula in a closed form, or even impossible to obtain this formula in closed form, but at least the problem is solved in principle. And something that you can do, for instance, is to solve these three equations numerically. Once you know the scattering data at some initial time t equal to 0. Okay. However, one can do better in a few cases. So in particular, obviously in equation 11.22 here, the complicated part here is this integral. So the first term coming from the continuous part of the spectrum. Because integrals are harder to compute than just discrete sums. So however, there are some potentials that we studied earlier this term which are such that the reflection coefficient vanishes for all wave numbers k. So those were the so-called reflectionless potentials. And when that is the case, when you have a reflectionless potential or an initial condition of the KdV equation such that the Schrdinger problem has a reflectionless potential, then the integral here in equation 11.22 goes away. And then F only involves discrete sum, which comes from the discrete part of the spectrum, so the bound state solutions of the time-independent Schrödinger equation. And so in that case, especially if you correct the typo here, so instead of infinity you have n, now you can write down, so you have a simple formula for F, and one can go back and take this equation 11.22, plug it in the Marchenko equation, and it's possible to solve for the integral kernel k and then compute the Schrödinger potential using 11.20. And so we obtain the KdV field at any given time t. So later on in the notes, in a part which we won't have time to cover, I precisely do that exercise, so you can read on if you're interested. So when you do that, essentially what you find is that the general solution, well, the solution of the KdV equation that you obtain is a solution which only involves solitons, and there are precisely capital N solitons. So there will be n different KdV solitons which evolve, they have different heights, widths, and therefore different velocities, and they evolve in time. They scatter through one another, and in particular, when the KdV time t goes to minus infinity or plus infinity, they're all far away from one another, and you can really see that they look like single solitons. So when the potential is not reflectionless and you have also the first term, it might be hard, as I said, to solve the problem exactly, so to obtain an analytic form for the KdV field. But one can still learn a few lessons, and that's what I would like to conclude with. So the general picture is as follows, and that again can be confirmed by looking at examples, which unfortunately I don't have time to cover, but you can read more about it later on in the lecture notes if you're interested. So there are two parts, as we've seen, to the spectrum of this time-independent Schrödinger problem. So there is a discrete part of the spectrum where the scattering data are the discrete eigenvalues mu n and the coefficient Cn. So when so that's the situation that I just described. When the reflection coefficient here is 0, we only have the second contribution, where the inputs are mu n and Cn. And when we plug it in this recipe, and we first find F, then we find the integral kernel K, and then from it we obtain the Schrödinger potential V, which is the KdV field. We learn that the KdV field indeed involves n right-moving solitons, which are hidden inside the initial data. On the other hand, if you have only the continuous part of the spectrum, then the scattering data consists of the reflection coefficients R of k. So now you only have the integral and no sum. And in that case, if you can solve the integral and then plug it into the Marchenko equation, find k, and then the potential V or the KdV field U, what you would learn from doing that is that the solution of the KdV equation U of x and t describes left-moving dispersive waves which are hidden inside the initial data. And in a general situation in which you have both the continuous and the discrete part of the spectrum, then the solution will involve both solitons moving to the right and dispersive waves moving to the left. And we can also say a bit more. In particular, let's go back to, so maybe this is a bit too small. So let me just focus on the second line here of equation 11.22 here. So we see that the dependence on psi and t goes in a form which is psi minus, say, some velocity times t. And here again, psi minus the velocity times t, where the velocity in a psi space is 8 mu squared for the discrete part of the spectrum, which corresponds to the pure solitons, whereas it corresponds to minus 8k squared for the continuous part of the spectrum, so corresponding to the dispersive waves which move to the left. So from that, we would conclude that the solitonic bits of the solution move to the right at velocities 8 mu n squared, and the dispersive waves move to the left at velocities minus 8k squared. But we actually have to be a little more careful because these are velocities in psi space, and psi was some auxiliary variable. And if you trace back what this means in terms of the actual spatial variable x and time t, it is not hard to see that the actual velocities are 1/2 of these. So a soliton, so once you have a scattering solution with wave number k, then that will lead to a dispersive wave which moves to the left with velocity minus 4k squared, whereas from a bound state solution with eigenvalue mu n, we obtain a soliton which moves to the right with velocity 4 mu n squared in a physical X space. Okay, so and finally, just to conclude, I would like to say that so this method of inverse scattering, which is in principle allows us to solve the initial value problem for the KdV equation, should be thought of as a sort of a nonlinear Fourier analysis. So why do I say that? Well, the link to Fourier analysis comes from this expression here for the function f of psi. So we see that the first term here is literally the Fourier transform of the reflection coefficient r. And so in particular, different waves with different wave numbers k are superposed linearly. And similarly here we have the discrete part of the spectrum, and you see that so now we have a sum instead of an integral, but that's just because k now is equal to I mu, and mu only takes discrete values. So still you can, in this expression here, you can superimpose different solutions coming from different bound states, so that they would contribute each term to the sum, and a different solution coming from scattering solutions, different values of k, and they will contribute to this integral. So this is all nice and linear, and it's really literally a Fourier transform. So what is nonlinear is that we're actually interested in the Schrdinger potential V, or the KdV field V, but that's obtained here from the integral kernel k that solves the Marchenko equation. And even though f essentially is a linear superposition of different contributions coming from the discrete and continuous part of the spectrum, when you solve equation 11.19, the resulting integral kernel k will not be a linear superposition of different contributions coming from the discrete and the continuous part of the spectrum, and therefore the same will hold for V. So the nonlinearity here is due to equation 11.19, which is the Marchenko equation. But the nice bit is that while the full problem is nonlinear, essentially many aspects of this inverse scattering method allows to use linear problems which allow the superposition principle to hold. Okay, so I will stop here. And again, if you're interested in looking at examples, you can read on in the notes and you'll see how the inverse scattering method using the Marchenko equation can be used, for instance, to obtain a solution with a single KdV soliton or multiple KdV solitons. But I will stop here. Thank you for your attention.